Okay. So we're gonna today finish up with our factors affecting pulmonary ventilation and we'll get into our gas exchange. Okay. So when we left off, we were talking about lung volumes. So just a little recap here, right? So we're talking about the air in our lungs, and we could see that we would separate it into sort of certain segments. So our normal easy breaths constitute our tidal volume, about 500 milliliters, but we have reserve volumes on either side. So you can breathe in more than easy breathing. So that's inspiration. So we have an inspiratory reserve volume. You can breathe out more than you do when you're easy breathing. So we have an expiratory reserve volume. So we can see that none of these actually overlap. We can see that we also have a little bit left in our lungs, even when we breathe out everything we can get out. And that's our residual volume. Okay, so those are our lung volumes. And if we add them all together, we get our total lung capacity. So the maximum amount of air we can hold in our lungs. Okay. So now we're going to talk about some more lung capacity. So you have one big slide with all the words. I separated it out so that we can look at it on the picture while we talk. And I posted this picture as an announcement, but I think it's just from your book. But in case you want to pull that up later. Okay. So our lung volumes that we went over were here. So now we're getting to our lung capacities, which are going to be adding together different portions of those lung volumes. Okay. So say we're interested in just how much someone can breathe in overall. We don't care really if it's easy or if it's hard, right? We just want to know everything that can go in. Okay. So you know you could breathe in an easy breath. So you'd be able to breathe in the tidal volume. You know, you're able to breathe in a little more on top of that, or maybe a lot more, your inspiratory reserve volume. So if you add those two things together, that's just one big long breath all the way. So that's your inspiratory capacity. So your inspiratory capacity is the total amount you can breathe in after breathing out. So we add those two volumes together to get this capacity. Okay. So we see that here. All right, our vital capacity is still going to be kind of about breathing in, but in this case, instead of from starting sort of at our resting point, we're going to say we breathe out as much as we can, and then everything we can breathe in like from the bottom there after expelling all the air we possibly can. So in addition to adding together our tidal volume and our inspiratory reserve volume, we now also need to make up for that deep breath out. Okay. So we are going to add together those two things that we just added together to get our inspiratory capacity. Right. So this was the tidal volume and the inspiratory reserve volume, but we're also going to add in that expiratory reserve volume here so that we get that full spectrum, right? So we breathe fully out and then fully in as much as we can. That would be our vital capacity. So basically all the air that we can move is part of our vital capacity. Okay. I'm going to flip to the next slide for myself, but you guys are staying on the same one. Okay. All right. So that leads us to our functional residual capacity, and then we can see that total lung capacity on there again. Okay. So our inspiratory capacity, everything we could breathe in from the bottom of a resting breath. Vital capacity, we breathe all the way out, then all the way in. Our functional residual capacity is going to be about how much air is hanging in the lungs when we're just kind of easy breathing. All right, so we know that our tidal volume is just the amount of air that we're moving in and out when we're easy breathing. Right, but we do have more air still in the lungs. Right, we're not moving absolutely all the air we could be moving, and there's some air that we just like can't move. Okay, so that has to do with our functional residual capacity. So we're going to add together that forced breath exhalation, which is our expiratory reserve volume, And then we're going to add in the residual volume, which is the amount that's just stuck in the bottom of the lungs that we like can't move at all with a given breath. Okay. And that's going to be our functional residual capacity. Okay, so those two things together are our functional residual capacity. And our total lung capacity is just that maximum volume of air in the lungs after you take the deepest breath possible. So we're adding together everything we can, right? So we need to add our tidal volume. We need to add the inspiratory reserve volume. We need to add the expiratory reserve volume, as well as the residual volume, because we're just trying to get that full measurement. Okay. So difference you'll notice between the lung volumes and the lung capacities, right? Lung volumes don't overlap. So you can think of them as like little units, right? Which is why we can give our lung capacities as adding together these pieces, okay? But we can see that our lung capacities do overlap, right? Like here, our vital capacity includes our inspiratory capacity plus some more, right? Our total lung capacity includes all of these things together. So you can think of those lung volumes as units, and then those lung capacities as like measuring full breaths in, full breaths out, things like that when you're actually looking at a person. Cool. So now we're going to talk a little bit about pulmonary function tests, and we're going to talk about obstructive and restrictive pulmonary diseases. So these are both two different types of diseases that can affect your lungs and affect how much air you're getting, but they work in different ways. Okay. So in an obstructive pulmonary disease, we'll start with that. We're going to be thinking about something that's changing the airway resistance. Okay. So we know that resistance is going to affect our flow because that's part of our flow equation, right? Okay. So if we affect this resistance portion, what we're going to be doing is changing how fast, essentially, we can move air in and out of our lungs, right? So we're changing those tubes, how wide they are, changing their radius, changing their diameter, okay? So when we see increases in airway resistance, this means that it is more difficult to breathe in because you've got a narrow little radius, but the somewhat unexpected piece of this is that because it's also more difficult to breathe out, you're going to essentially end up with like extra air stuck in the lungs at the end of a breath. So you're going to see with obstructive pulmonary diseases that the lungs start to get like overinflated. And this is because it's much more difficult to expire, to breathe out than usual. And usually, right, we can just relax essentially. And that with that recoil, our air moves out, right? That's not going to work really with an obstructive pulmonary disease because we have issues with the airways, right? So some of that air is going to stay in the lungs, causing those lungs to get overinflated. That's because of that difficulty with expiration, with moving air out, in addition to the difficulty moving air in. Okay, so that overinflation in terms of our lung volumes, lung capacities, we're going to see that our functional residual capacity is going to be going up, right? So we're going to see that air staying in the lungs at the end of our breath. That's our functional residual capacity. Okay? And we're going to see that the vital capacity, so the overall air that we can move, essentially, our vital capacity is going to be decreasing because of that change to the airway. Now, the restrictive pulmonary diseases don't have to do with the airways, they have to do with the lungs themselves. So in our restrictive pulmonary diseases, we're thinking about that concept of compliance. So remember, compliance had to do with the fact that we have a sort of trade-off between volume and pressure. We have a trade-off between compliance and elasticity in the lungs. So when we say that the lungs have high compliance, what we mean is they're able to hold a lot of volume without much change in pressure, which is great for us because that means we don't have to work too hard. We don't have to create too big a difference in pressure in order to breathe air in and air out. If we have decreased compliance, what we're saying, right, is we're getting more like an artery than like a vein was the last time we talked about compliance in our previous unit, right? So we're making it so that we're going to need a lot more pressure to see the same changes in volumes, right? So you'd have to work a lot harder, create a lot more pressure in order to get to the same lung volume, okay? So when we have issues with lung compliance, we're going to see that our total lung capacity is going to decrease, okay? And we're also going to see that our vital capacity is decreasing. So some of the symptoms of these two types of diseases are going to overlap, but we're going to see some differences. So some of the ways we would look at these are using pulmonary function tests of various types. Okay. So pulmonary function tests are testing how are the lungs working. Okay. So we're going to do a couple different things than before, right? The first thing we're going to do with our pulmonary function test is we're going to take a forced vital capacity, or an FVC. Okay, so what we're going to do there is we're going to take a maximum inhalation, so as deep as possible, and then you're going to blow out as fast as you can. Okay, so the forced vital capacity, we're breathing all the way in, and then we're breathing out as fast as possible. Okay, so here we see a normal curve for our volume that we're breathing out as we're getting to that forced vital capacity. So the forced vital capacity is going to be the volume we eventually get to as we're breathing out. Okay, so that's labeling this point in this top image. Okay, so we can see we breathed all the way in, and then we breathed out 1 liter, 2 liter, 3 liter, 4 liter, flattened out at 4 liters. So that would be our forced vital capacity. Okay, now when we see a low forced vital capacity, this is usually going to be an indicator of restrictive pulmonary disease. Okay. The other thing we can measure is forced expiratory volume. Okay, so the forced expiratory volume is similar, but what we're doing here is we are making a time point of a second, right? So we're not going to be looking at the total amount, but we're going to look at the percentage that we can get to in a second. Okay, so this is our forced expiratory volume given as whatever this number is divided by that number, giving us that percent. Okay, so we can see that under this normal condition, all right, we should be getting about 80% of the air out. 80% of our forced vital capacity is being expired within a second. And then we see the flattening out of the curve. We can see that in both our obstructive and restrictive pulmonary disorders, actually, we do have changes here. Okay, so here we can see that in both of these, we're getting a little slower, right? So we're going to have a lower number for both of them. But what's going to be a really noticeable point for the obstructive pulmonary disease is that it's going to be less than 80%. Okay, so these are just kind of like benchmark numbers. So we can see that in our obstructive pulmonary disease, right, our airway is narrowed. We're having trouble getting air out, so that's going to be low. Okay, we do eventually get all the air out in an obstructive pulmonary disease, versus in the restrictive pulmonary disease, we actually never get to that total normal volume. Okay, so that's what I actually think is the most interesting thing about these curves. So we can also see that when we look at this next image, which is of peak expiratory flow rate. So this is just another way we can measure this. So instead of being in volumes, this is in liters per second, right? So how much air is actually moving. Okay, so we can see normally we're going to have a peak at 7 to 9, depending really on the size of the lung, that peak expiratory flow rate, and then gradually tapering off. Okay, we can see in both the restrictive and obstructive diseases, we have differences here. Okay, and we can see that same sort of pattern. So we do have some change here to that flow rate in both our restrictive and obstructive diseases. But we can see in the obstructive disease, which is the one where we have the issue with resistance, right, that this is much lower. That flow is really impacted if we look at that peak expiratory flow rate. But we can also see that that total volume is eventually getting to kind of the same rate as our normal curve, versus with our restrictive disease, which is when we have issues with compliance, right? We do have some impact on that peak expiratory flow rate, right? But we actually never get to the same volume as we did with the normal condition, right? And this is because we need that big pressure difference to make up for this decreased compliance. And we just can't make that big a pressure difference necessarily. Right. So the next thing we're going to look at is alveolar ventilation. So we're thinking about like lots of lung metrics, basically, adding in all these concepts. So we've thought about, okay, our lung volumes, so how we can add together these different lung volumes to get different lung capacities. We've looked at some pulmonary function numbers to tell whether we have obstructive or restrictive diseases. And now we're going to start thinking about how much air is actually getting into the respiratory system any minute. So we're thinking about this from the level of the alveoli. Okay. So when we talk about the minute ventilation, we're talking about the total volume of the air entering and leaving the respiratory system any minute. And we're going to be thinking like easy breathing. So we're going to be adding together our tidal volume, so just that 500 milliliters in and out easy breathing, times our respiration rate, which is just like your heartbeat. It's the number of breaths someone is taking per minute. So you watch them per minute, count how many breaths they took. That's the respiration rate. Okay. So we're going to have a volume times the time. So we got a volume for each minute. So that's our minute ventilation. But if we're thinking about the gas that's available to your body, not all of that is going to be, it's going to be a slightly different perspective, because we're going to have that new air kind of mixing with the air that is already in the alveoli, right? So we're going to have a component of dead air, essentially, sort of dead space, air that we've moved gases in and out of already, that is mixing with the new air that you're bringing in. So when we think about our alveoli, we need to account for that, right? So remember that we have a conducting zone and a respiratory zone when we're talking about our airways, right? So the conducting zone was like the air in your nose, in your mouth, in your trachea, in your primary bronchi, secondary bronchi, tertiary bronchi, and so on, until we get to those respiratory bronchioles, right? We don't have gas exchange happening until we get to the respiratory bronchioles. Okay, so that air in the conducting zone doesn't cross cell walls, doesn't get into your blood. It's not participating in the gas exchange, but some of it still is in your body, okay? So we think of that conducting zone as anatomical dead space. We have approximately 150 milliliters of air in that dead space. Okay. So what we're looking at now when we're looking at alveolar ventilation, so the alveolar ventilation is now thinking about the air that gets into the alveoli specifically, rather than just the air coming into your lungs kind of generally as a unit. So we're thinking about how much air is getting to that respiratory zone kind of. Okay. So we're going to step through, but we're going to be thinking about, in terms of this diagram, we're thinking about this little neck. We're going to be thinking about that as representing our conducting zone. And then we're going to think about this round ball as our alveolus, so our respiratory zone, essentially. Okay. So we're going to step through. We're going to see that when we start out, right, we're going to have fresh air outside your body. We're going to have old air filling up that anatomical dead space. Okay. And at the moment, we don't have anything in our alveolus to begin with here in figure A. Okay. So we're going to step through next. We're going to take a breath in. Right. So when you take a breath in, we're going to think about essentially pushing or pulling that column of air down, right? You can't actually take fresh air from outside and like skip it straight down to the bottom of the alveolus, right? It has to go through the tubes. So all we can really do is move this column up and down, okay? So what we see when that happens, when we move this column, right, is as we breathe in, we're pulling new fresh air in, right? But what actually moves into the alveolus first is that dead air that was just in the conducting zone, right? So we just pulled everything down, right? So we have some fresh air entering the alveolus, and we now have some fresh air in the conducting zone right here, but we also have a portion of dead air that has entered the alveolus here. So next thing that happens is we have our exchange with the blood, which is going to be our next topic, okay? So what we can see happening here is some of our air we consider dead air, and by dead, we mean we took the oxygen out, we put carbon dioxide in already. So that was from the previous breath, essentially, right? So we're kind of done with this section of air, but the rest of this fresh air is now going to participate in gas exchange after our inspiration, right? So we are now going to be pulling oxygen out of it, right? Pulling oxygen out, feeding carbon dioxide in, okay? Until all of the air in the alveolus has participated in gas exchange. So we have that original dead air, and now this new fresh air that had oxygen, didn't have that much carbon dioxide, has now we've reached equilibrium with that original dead air. Okay. So we've done gas exchange with everything that was in the alveolus, but the air in the conducting zone, nothing. We don't have the ability to do respiration in the conducting zone. So this is still going to have all those original properties. Okay. So then for our next trick, right, we're going to breathe out. And that's how we get to that original image. After we expire, we're breathing as much out as we can, right? But some portion of this dead air that has already participated in gas exchange is going to be in our bronchi, in our trachea, just making those spaces stay open, right? We don't want a vacuum there. We don't want them to collapse, right? So they are filled with air, but that air is old air that doesn't have nice, fresh oxygen in it, and it's full of carbon dioxide. Okay. So this means that when we think about the air available in the alveolus for gas exchange, it's not as simple as thinking, okay, we breathed a new bit of fresh air in, we have all of that in order to do gas exchange. We have to account for the fact that this air that was in the conducting zone has already participated in gas exchange. So we've removed its oxygen, we've filled it with carbon dioxide. So it's not going to have the same properties as that fresh air that we're breathing in at the top of the column. Right. So this means that our alveolar ventilation looks a little different than our minute ventilation. So I'm going to scroll back up and just remind us what minute ventilation was, because I know that was a new topic already. All right. So our minute ventilation was just talking about the volume of air that entered and left in any given minute. So that part should be easy because it's just an easy breath, the tidal volume, times the number of breaths per minute. But our alveolar ventilation, we have to count for this mixing of air. Because for our alveolar ventilation, we want to be thinking about what's really available for gas exchange, okay? So for our alveolar ventilation, we're going to take that value for the minute ventilation first, right? So that was our air that we were breathing in, that tidal volume times the respiration rate. But we're going to subtract out the dead air, right? Because what we care about is the gas exchange part. So this is going to be our dead space volume, which is probably about 150 milliliters. And then again, times the respiration rate, because we're still carrying per minute. So that's just the number of cycles of breath per minute. So the alveolar ventilation is not exactly the same as the minute ventilation, because we have to not include that dead air because we don't care about that dead air, by which I mean that dead air isn't bringing us fresh oxygen. It's already full of carbon dioxide, so it's not going to help us with our gas exchange process. So that's why our alveolar ventilation metric is going to look a little different than our minute ventilation. Okay? So minute ventilation is all of it. Alveolar ventilation is just this nice fresh stuff getting to our alveoli. Okay. So now we're going to move right on and think about what we are doing with those gases that we are bringing to the alveoli. So we're going to start to think about the diffusion and the exchange of gases. So I'm going to orient us first to what we're talking about, like our big picture view. Okay, so our big picture view, so that we know that we have our alveoli, which is the primary part of the respiratory zone where our gas exchange is happening, right? So we're bringing in some amount of fresh air, right? If we want to measure it, we'd use that alveolar ventilation number where we subtract out how much of that was mixing with the dead air, okay? So we're bringing in nice fresh air in some quantity to the alveoli. And the reason we're doing that is that we have tissue out in our body, cells out in our body that are doing stuff, right? They're doing their internal respiration, their cellular respiration, where they're taking in oxygen, using it to convert glucose into ATP, essentially, right? So they're using oxygen and producing carbon dioxide as a byproduct down at the bottom of this image, okay? So we're bringing in new air that has new gases in it, and we're using air at the level of the tissue, essentially. We're using those gases and expelling waste products, okay? So our big picture of gas exchange, gas transport, right, is that we're going to be moving oxygen into the blood from the alveoli, okay, at the same rate as we're using it at the tissue. Right, so we're basically just trying to replace that oxygen that we're using, okay? And same deal with our carbon dioxide. Right? Our carbon dioxide is our byproduct, our waste product of cellular respiration. So here we see we're producing it at 200 milliliters per minute down at the tissue. So we want to export out that waste into our air in the alveoli when we do gas exchange in the lungs. So we're just trying to keep our amount of gas the same in our blood, keep same consistent available amounts of gases in our blood as you breathe in and breathe out, okay? And that doesn't mean we're going to have the same concentration in arteries as in veins, right? Because the arteries are going to need to be carrying more fresh oxygen before it gets used. And so then you'll see less in the veins versus our carbon dioxide, right? You're going to have a lower amount in an artery. Then as it passes tissue, it's going to soak up some carbon dioxide, carry it back to the heart through the veins, ultimately send that to the lungs, get that carbon dioxide into the air in the lungs so that you can breathe it out. So we will see that when I say we're keeping levels constant, what I mean is that if we're thinking about the arteries, we're going to have constants, right? So we're going to expect 1,000 milliliters per minute of oxygen and 2,500 milliliters per minute of carbon dioxide in an artery versus in a vein, we'll have different levels, right? So our oxygen will be lower because we removed oxygen at the tissue. Our carbon dioxide will be higher because we gave off our waste products and are sending those out to the lungs here. Okay. But this does mean that any of our organs coming off the side of the system, right? Any tissue out in the body should expect a certain amount of oxygen, right? It's going to expect that 1,000 milliliters per minute if it's getting fresh arterial blood, right? And it's going to expect a certain amount of carbon dioxide that it can then jack up as it gives up its additional waste product, carbon dioxide. Now, if we want to compare these different amounts, we might compare how much carbon dioxide is being produced versus how much oxygen is consumed. And we would just call that our respiratory quotient. So we just divide one by the other, right? So our ratio of carbon dioxide to our oxygen would be like, that's what we're looking at when we're looking at the respiratory quotient. So that's our like big picture view of what's happening as we think about gas exchange. And we are going to go through all of these little bits step by step, but that's essentially the process that we're trying to understand. Okay. So when we're thinking about those gases diffusing, okay, so you know that you breathed in, you inspired air because you contracted your diaphragm, it went down, use those external intercostals, your rib cage expanded, you have a big volume for your thoracic cavity, right? Which means you have a low pressure, it's pulling air towards it because you have a drop in pressure relative to the atmosphere. So you got some air into your lungs, into the alveoli, okay? So now that we're thinking about diffusion and transport of these gases, we have to think about what we're doing with the oxygen and carbon dioxide in that air, okay? So we know that the walls of our alveoli are primarily made up of those type 1 alveolar cells, right? Those were the ones making up our epithelial lining, okay? All right. And we know that we have lots of surface area in these little bubbles, all right? And we only have one additional little cell layer to cross, that endothelial layer of the capillary. And this type 1 alveolar cell is glued on to that capillary endothelial cell by our basement membrane. Okay, so we got a nice thin layer for our oxygen to dissolve into the plasma, okay, and our carbon dioxide to dissolve, to dissolve out, okay? So they're both just diffusing because they're both non-polar small little gases. They can get across a cell membrane perfectly fine, okay? There are, however, going to be some factors that affect how much oxygen is going to go into the plasma and how much carbon dioxide is going to come out and go into the alveoli. So we're going to be thinking about something called partial pressure. And we're also going to be thinking about the solubility of those gases in the liquid, okay? So they are going, right, from being mixed in with other air here in the alveoli versus the plasma, right, is fluid. So they're dissolved into that fluid once they're in the capillaries. So we have some things we need to think about when we think about that process. So to understand the partial pressure of the gases, first we're going to think about that ideal gas law. Okay? So before we were looking at this, because we were looking at that trade-off between the pressure and volume, right? We had a sort of inverse relationship between the pressure and the volume here. You can see we divided by the volume, right? Which is why we have that trade-off. The pressure goes up, volume goes down, vice versa, okay? And what we might also notice now that we're thinking about these gases as gases and what are they doing in the alveoli, what are they doing in the blood, okay? We're going to notice that the pressure of the gas is dependent partially on that volume, but it's also dependent on our number of gas molecules, and it's going to be dependent on the temperature. Okay. So we're also going to pick out these parts now. Okay. So the pressure of the gas depends on the volume of its container, but also on how much of the gas there is and how warm it is. Okay. Okay. So when we think about the air we're breathing, the air you're breathing is not pure oxygen, right? That's why sometimes people need to use oxygen tanks, right? Sometimes we need to change the composition of the air people breathe under certain conditions, right? So many gases, including the air we breathe, are mixtures of different molecules, different types of gases, okay? So when I think about the partial pressure of a gas, what we're saying is that the air around us, right, all of it together has some pressure, right? We saw that atmospheric pressure was 760 millimeters of mercury, right? We set it to 0 when we were doing our relative pressures for the lungs, but it did have a value all on its own. But if we want to track a specific gas, it's only responsible for part of that, essentially. So the partial pressure of the gas is just referring to the proportion of that pressure that's due to that individual gas that you're tracking. So we can think of that total pressure as just being broken up by the pressure of oxygen, the pressure of nitrogen, the pressure of carbon dioxide, et cetera, okay? So whatever gases make up that total gas around us, right, are all going to add into that pressure, okay? So we can express this as a fraction or percent, essentially. So the partial pressure of that gas, okay, we're going to take our total pressure, okay, and then we're going to multiply it by the percent made up of that gas, right? So if you have a gas that's 50% of the atmosphere, right, you just multiply that total pressure by 50% to get your partial pressure of that gas, okay? So we're thinking about our total pressure as adding up partial pressures for multiple gases. So when we think about the air around us, not only is it not mostly oxygen, it's actually mostly nitrogen. So about 79% of the air around us is made of nitrogen. 21%-ish is oxygen. And then we also have some carbon dioxide, maybe we have some helium, some argon, other trace gases. Depending how humid it is outside, we may have water vapor as a gas in the air around us that can also make a difference, okay? So the composition of air is going to be made up of a number of different gases. The ones we're primarily paying attention to are the nitrogen and the oxygen, at least at first, okay? So when we think about the partial pressures here, right? So we're thinking about our pressure of the air, right? So before we had our atmospheric pressure, right? So this is that same number, okay? That's 760 millimeters of mercury, okay? So we're saying that 760 millimeters of mercury, that pressure is the pressure of the nitrogen plus the pressure of the oxygen in the proportions that we see those gases, okay? So to find that partial pressure of nitrogen, right, we know it's 79% of the gas around us. We know that the pressure of the gas around us in total is 760. So we just multiply 760 times that 79%. So we just see 79% as a decimal here. So we'd get a partial pressure for nitrogen at 600 millimeters of mercury, okay? So if you see P and 2, P, O2, P, we gave one for CO2, which we will think about later, right? That's just talking about these partial pressures of the gases. So it's telling you that you're tracking that gas specifically, okay? And likely that it's a part of a total pressure, okay? But we're tracking just one of them. Okay? So to do that, we just multiply times the percentage. So the air in the environment around you is only like 0.03% carbon dioxide. So when we're thinking about the air out in the atmosphere surrounding us, we don't really have to think so much about that partial pressure. Okay? However, as we humidify air, okay, we're going to see a change. Okay, so remember that one of the things that's happening in our conducting zone as you're breathing air in, right? You're warming that air up and you're actually humidifying it, right? So you are changing that air a little bit to make it more friendly for your lung tissue, right? So it doesn't like hurt your lung tissue, okay? So water as a gas affects the composition of air if you're out in the environment around you, but also your body is a little bit changing the composition of that air as you breathe it in, okay? So when we're thinking about the air you breathe, we do want to think about humidity as well, okay? So at 100% humidity, the partial pressure of water, that water vapor, H2O, is about 47 millimeters of mercury, okay? So this means that our composition of the air is going to change in terms of these partial pressures when we have this humid, warm air, okay? So we're still thinking about being at equilibrium with the air around us in terms of pressure. So we're still going to use that total pressure of 760, right? But now we're looking at not just nitrogen, and oxygen, but we're also looking at that water vapor. So water in gas form. Okay. So at 100% humidity, our partial pressure of the water vapor has taken away a little bit from those partial pressures of the nitrogen and oxygen. Okay. So these 47 millimeters of mercury taken away from those other proportions. So at 100% humidity, these are about the values we'd expect to see. So 47 for our water vapor, 563 for our nitrogen, 149 for our oxygen. And we put the carbon dioxide on here just to be thorough. You can see that that's a very low partial pressure compared to these other numbers because carbon dioxide makes up so little of the air around us. Okay. So when we track partial pressures in physiology, we are often going to be talking about partial pressures not in a gas in the air around us, but we're instead going to be talking about like partial pressures as a measure of the gas in your blood. So this means we're going to have to do another step. Okay. So your gas molecules, they can exist in gas form, but they can also dissolve in liquids, but they don't all dissolve in liquids equally well. Okay. This is actually good for us, kind of, because we saw what was going on with the carbon dioxide, right? It would be very weird for the carbon dioxide with those low partial pressures in the environment around us. Those don't at all match what we're going to see in our bodies, okay? So the ability to dissolve a gas into a liquid is going to depend on the properties of the gas as well as on the properties of the liquid, okay? We can still think about them exerting partial pressures though. So we can use a partial pressure measurement for a gas in gas form in your lungs or in the environment, or we can give a partial pressure of a gas like dissolved in plasma, okay? And the partial pressure of the gas in the air is going to affect the amount of gas that goes into solution. When we're thinking about physiology and gas exchange, we're thinking about blood, we're thinking about plasma, okay? Now, the thing that we do want to realize is that the partial pressures of our gases, whether vaporized or dissolved, are going to come to equilibrium eventually. They're going to come to the same amount if you let them fully exchange with each other. Okay. So now we have something called Henry's law. So this is just sort of detailing that out mathematically. So we can see that our moles, our concentration of the dissolved gas in a liquid, is equal to the partial pressure of the gas in the atmosphere times a constant, okay? So we could calculate essentially the concentration of a gas like in your plasma if we knew the value of this constant and we knew its partial pressure in the atmosphere. Okay? So why we really care about this background is because we're tracking oxygen and carbon dioxide. We're tracking them in the air around us. We're tracking them in our alveoli, and then we're going to track them in our blood. So in the arteries, in the tissue, then in the veins coming back. Okay. So the important thing to know, therefore, is that oxygen and carbon dioxide do not have the same solubility in liquid. Okay. So our carbon dioxide has a way easier time dissolving in water and therefore in blood than oxygen does, okay? So we would say that the solubility of carbon dioxide is much greater than the solubility of oxygen in water and therefore in blood plasma, okay? So if we were to say that we have a partial pressure of 100 for either oxygen or carbon dioxide, what we're saying, we had that, okay? So this was how we would figure out the molar concentration of the gas with that Henry's law from the previous page. All right, so what we're saying is that if we're tracking oxygen with a partial pressure of 100, okay, all right, we'd get about 0.15 millimoles per liter. All right, so 0.15 millimoles per liter would be our constant times our partial pressure of oxygen. Okay, versus for that same partial pressure, right? So if we had a partial pressure for carbon dioxide of 100 times its own constant, we'd have a much higher amount dissolving into our fluid. Okay, so you're going to expect to see different constants for different gases. Going briefly on that, because calculating those out is not a major thing that we need to worry about for the purposes of this class, but like understanding why in this relationship is something that we want to be able to do. So we'll talk about this picture and then we'll break, but I just want to show you. So what we're looking at here is we have oxygen partial pressure in the air coming to equilibrium with oxygen in the water. So equilibrium, they've both reached a partial pressure of 100. Okay, versus on our next slide, when we look at a picture of the other version, the carbon dioxide, we can see for that same partial pressure of 100, when we come to equilibrium, more molecules of carbon dioxide are in the water. That's because the carbon dioxide is more soluble than that oxygen. Okay, so we'll break here. Wednesday is community day, is that right? Okay. So what I'm going to do for us then is this evening, I'm actually going to put up our practice test for the exam so that you can work through that at your leisure and use that time. And we will go over and finish at least this concept on Friday so that we're a little bit further. I'll be very specific about what we need to cover for that for the exam. I'll give you one or two exact question types that we would cover. Okay.